This is on. Hopefully you printed the sheets off. I did skip some pages in the sheets that I put online, just because we don't need them all. But momentum. So momentum has to do with Newton's laws. And Newton combined a moving object's mass and its velocity in an expression that he called quantity of motion. We now call this quantity of momentum and give the symbol P with a line over it. The momentum of a moving object is given by the equation. Okay, so essentially what we are doing is we're measuring. So when it comes to collisions, and this is why it's so unfortunate that we don't do, we aren't in school here, because I like to run this into the concussion movie and the video and go through it with you, because what they're finding now, obviously this is really old material with momentum, but what they're finding now is there are obviously a greater emphasis put on concussions and concussion protocol. And the questions are being asked. So like, what is the difference? Like, why now are concussions so prevalent compared to, let's say, 20 years ago or 30 years ago? And primarily the number one reason is the testing for it. They test for concussions a lot more now. They have baselines. So people do baseline testing on their brain, and for athletes at least. And so they'll go into their training camps and they'll do baseline protocols. And so they'll know, where after they've taken a hit or whatever. But why is it? What is the reason that concussions are more prevalent? Because they clearly are. It's happening at a greater frequency. Well, basically the best explanation that you could possibly use is the momentum and the amount of motion that's happening here. Okay, so the greater the momentum, the greater the collisions. And look at the two variables that affect it. The first variable, mass. Well, if you took the average size of an athlete now compared to an average size of an athlete 10 years ago compared to 40 years ago, all right, it's going to be significant. Athletes are bigger, much, much bigger right now. And that's because training is a whole lot different. And the other major reason momentum and collisions are more dangerous now is the speed. These guys are not only bigger, but they are so much faster than what they used to be. And again, not saying that the guys couldn't skate the same in the 90s and the 80s and the 70s, but the difference being technology for sure is being one of them. All right, the technology has changed in terms of hockey, especially the skates have changed so much that they are allowed to be faster. But the training mechanisms that they're using now compared to what they used in the 70s, 80s, and 90s and the 2000s are significantly different. So the big reason why concussions are going up is because the two things that affect how serious a collision is, the mass and the velocity. So you make them bigger, you make them faster, you're going to have bigger collisions. And the same goes for the sport of football. All right. Obviously, football's taken it to a new level. Why? Well, those guys are bigger and faster, and they're hitting harder than they ever did. They have more momentum, and the collisions are greater. So the other thing that we do with momentum is we look up. I go online with sports science and look up Ray Lewis versus the battering ram on sports science. So essentially what they do is they take a SWAT police man with the battering ram, and they compare the amount of force he has with the battering ram going through a door. Then Ray Lewis, who's an NFL football player, a linebacker, who is about, I think they say he was around 285 pounds or so, and can run 40 yards in just over 4.5 seconds. All right. The amount of force that he could generate in 2 full strides was about 1.5 times greater than a battering ram by a SWAT team member. And again, his size and his speed are is the greatest significance here. And so when we look at sports and we look at athletes, the biggest reason why concussions occur is using Newton's laws. For every action, there's an equal and opposite reaction. Well, if you get hit by somebody or you hit somebody, you still feel the effects of it. This is the thing that people don't get. I can throw a body check on somebody and I'm going to feel the effects of it, no matter how it does. Why? Well, inertia. What happens is my brain keeps going, all right? My body stops suddenly and your brain bounces. So it all can be explained using Newton's laws, okay? And momentum is the reason why they are much greater than what they ever used to be. The other thing that we talk about is impulse. So impulse essentially is found by taking, I'm just going to change this. I was looking at the textbook, but it's somewhat a change of momentum. All right, and impulse is found by taking the amount of force over a given amount of time. So where we talk about impulse and its greatest significance is if you're falling, let's say, all right, best example I can use, you're coming off a diving board and you're jumping into a swimming pool, okay? If you make yourself as small as possible, all right, the impact will be on, let's say you're just doing your feet are going, your own feet first. So the impact is on your feet. So somebody's jumping off a cliff, the impact is on your feet, okay? But it's a short amount of time that's impacted, so you don't slow down as much, but it's jarring to your body. All right, now you take a gymnast who is falling backwards. All right, they do a flip and they're out of control and they fall. What they're told to do is get their body expanded. You are trying to generate the amount of time and spread out the amount of force on your body to take the impact away from little parts of your body. All right, so impulse is the amount of force over a given time. Okay, when I'm hitting a golf ball, again, I'm doing all these sports simulations, but you guys get it. Or you're hitting anything. You're hitting a volleyball, let's say, or a golf ball. Okay, the whole point is to impact it with as much force and over the greatest amount of time possible. So you want if you look on page 291, they show a slow motion of the club head hitting the ball. Well, you want the club face to stay on the ball as long as you can with the most excessive amount of force that you can to create that speed and off the club head so that the ball goes much further. Okay, so this is what we refer to as impulse. And then they go into, we don't work a lot with impulse, but they go into it and they show it using graphs. But I think I might have got rid of your graphs for you. Okay, so working with these two. So now what I can do is I can look at how impulse and momentum work together. Because impulse is essentially the change in momentum. So if I take and change, of course, if I take m2 v2 and subtract m1 v1, I'm finding my change in my momentum. And that is the same as my impulse, which is force times time. So if you open up to page 296, it says on the top left corner, it says, Newton's original statement of his second law, force is equal to change in momentum over time, is actually more general than the more familiar form of force equals mass times acceleration. Since it includes cases where the mass changes, an example of such a case is an ascending rocket. As the rocket rises, it loses its mass as it burns fuel for propulsion. Okay, so what they're saying is for impulse, for force equals change in momentum over change in time, they're saying like a rocket that goes up into the air, all right, is getting more momentum as it goes up because it's losing, or sorry, be getting less momentum as it goes up because it's losing its mass. All right. So the propulsion is happening. So the force from the thrust of the rocket engine is occurring. But as you go up, you're losing momentum because you're losing your gases. So that's some of your mass. Okay. So what we are going to do is we are just going to simply work with this. How change in momentum and impulse affect each other, and we're going to look at a few different examples as to how it works. So the first question that we're going to look at that pertains to momentum and impulse says, what velocity would a 40-kilogram child sitting on a 40-kilogram wagon acquire if it is pushed from rest by a force of 75 newtons for 2 seconds? Okay, so we have a 40-kilogram child sitting on a 40-kilogram wagon. So we got a mass of 80 kg. It's pushed from rest. If we need this, 0 meters per second. We're looking for V2. We have a force of 75 newtons. We have a time of 2 seconds. Okay, and it wants us to calculate. So before, when we did finding our V2, we usually needed the acceleration to find the V2, all right, or the distance that it traveled. But now what we're looking at is we're using forces with it. Okay, we've done something similar to this already. Okay, we did this back in our forces unit in grade 11. So I need to find out how much force, and actually the question that you'll remember that we always struggled with was the skateboard one, where you had to propel the skateboard, and then it glided for 1.5 meters. So we've done something very similar to this. So this is going to be done a little bit easier than that question was. So our change in momentum is force times time. Okay, that's impulse. So we're looking for our impulse. So our impulse is the amount of force acting on something over a given amount of time. Okay, so M1, so I've got 80 times V2 minus 80 times 0 is equal to my force, which is 75 times 2 seconds. Okay, can we then find out what V2 was? So V2 is equal to 75 times 2 over 80. So whatever 150 over 80 is. So our speed, based on our change in momentum, is 1.875 meters per second. And it is, because it's a speed, we should add direction to it. So it would be in the direction of whatever the force is. So it says that what velocity will, if the wagon is pushed, so if you're pushing on the wagon, it's in the direction of the motion. Okay? We're all right? I think you're going to find this fairly simple. We did very similar stuff to this in grade 11. What average force will stop a 1,000-kilogram car in 1.5 seconds? So stop means V2 is 0. 1,000 kilograms is your mass. Time is 1.5 seconds. If the car is moving at 22 meters per second, initial velocity, 22 meters per second. Looking for my force. So 1,000 times 0, subtract 1,000 times 22 equals my force times 1.5 seconds. force equals. Okay, so I have 1.5, minus 22,000 divided by 1.5. So the amount of force required to stop that vehicle from 22 meters per second in 1.5 seconds. So again, we've done stuff very similar to this. We could have, if we were to do this before, I would have said, okay, the first thing you do, you've got V2, you've got V1, and you've got time, is find your acceleration. And then once you found your acceleration, you would times it by the 1,000, and you would end up with the force. So you could do that question exactly like you would have learned in grade 11 and still got the same answer by using your original 5 equations. So we're going to go back to that equation sheet that we used before, and we're going to work through it. Okay. Now, what we're going to do now, okay, is bring this together and understand why things are happening. Okay, so now we're going to look at about 3 different varieties of questions based on momentum. Okay, the first one is if you have one object that's moving and it comes into contact with another object and they collide. Okay, and I want to find out what the momentum is, or I want to find the velocity after the fact. So an example is if you have an engine on a train and it's going to couple with a stationary car. So the engine's moving in this direction, okay, and my V2 is 0 here. This guy's at rest. So the engine moves towards it, it hits it, they join up, and they move together. Okay? There's one scenario. A second scenario is 2 objects coming together and colliding after they hit. This one might go this way, this one might go that way. Possible scenario. Okay? All we are going to do is we are going to learn how to calculate what happens when objects come together and they share momentum. Okay? So this is all based on the law of conservation of momentum. And the law of conservation of momentum says this, that the momentum before a collision is exactly the same as the momentum after a collision occurs. Okay? When you study chemistry, you looked at the law of conservation of energy, where when you had the amount of energy before a reaction occurred is equal to the amount of energy after a reaction occurred. It's the same thing for momentum. So my momentum beforehand is equal to my momentum after. I designate that, well, I call it prime, P prime. Basically what it is just a tick to tell me that this is the momentum after a collision occurs. If the net external force acting on any object or system of objects is 0, then the total momentum of the object or system of objects remains at a constant. Okay, so when you're finding momentum now, all right, when you're finding momentum, if you have 2 objects, let's say I have 2 objects, I could say I can add the momentum together beforehand. So that's my momentum beforehand, and that should equal my momentum after. Now, sure, there's going to be losses. All right, for example, excuse me. For example, 2 cars colliding. There's going to be some energy lost in heat. There's going to be some energy lost in sound. There's going to be different ways, but what we are doing is we are doing the best we can to calculate what the momentum is going to be after a collision occurs. Now, I'm going to show you a secondary equation, and the secondary equation basically is, for the first example I showed you, if two objects hit and they stay together. Okay, now this equation is not a lot different. I still have the momentum of both objects beforehand. But if they come together, they're moving together. Therefore, they're going to have the same velocity. So this is if I have a collision of two objects and the objects stick together. Okay? If they stick together after the collision, then I only have one velocity and my momentum is combined between them. All right? So this is what we are going to use right now to help us solve a few problems. So on page 300, it says a loaded railway car of mass 6,000 kilograms is rolling to the right at 2 meters per second. So M1, V1, 6,000 and 2 meters per second to the right. It collides and couples with. So the moment it says couples with, it means it joins together. Couples with a car mass 3,000 kilograms rolling to the left on the same track at 3 meters per second. Okay, so M2, 3,000. V2 is minus 3 meters per second to the right. Now, I don't want to confuse you. I put this one as to the right. I just need to make it positive. I don't necessarily need to write it in there, but you have to understand, or you have to remember that you've designated to the right as positive and to the left as negative. Well, we always do that, so it shouldn't be any big deal for you. Okay. They couple together, and it says, what is the speed and direction of the pair after the collision? Okay, so I have one car moving this way. I have a secondary car moving that way. And at this point, they're going to join together. And I need to determine which direction that they're going to go based on my momentum. So M1, V1, 6,000 times 2 plus 3,000 times negative 3 is equal to my combined mass of 9,000 because they couple together times V prime. 12,000 subtract 9,000 is 3,000. 3,000 divided by 9,000 is 0.33 meters per second. And it's positive. So if it's positive, which one of the directions did I make positive? I made right positive. So the answer to the question is they will couple together and move to the right at 0.33 meters per second.
Mr. Chairman,
Yeah.
Did we do this last year?
We may have started it last year. Yes.
So I'm pretty sure we did almost that exact same question last year that I remember.
Okay. Well, then life is going to be easier for you because I need to go through it before I get into energy. So maybe we'll just go through it fairly quickly. We won't go through all the review questions. We'll just do the problems. But I wasn't sure. I thought we had touched on it last year as well. Did you watch the movie Concussion last year?
Yeah, we did.
Okay, so we did go through it. I wasn't sure if I did it with you or the other group. Okay.
Was that the football player and stuff?
One at a time here. Rory, go ahead.
What was that the one with the football player and stuff?
Yes.
The movie?
Yeah.
Okay.
Okay. So we have gone through some of this, so I'll go through it. The reason I want to go through it is I want to do the vector part of it, because we're going to get into work and energy right away as well then. So I'll go through this quickly this week, and we'll just go through the practice problems. We won't go through all the review questions or anything to do with that. Okay?
Mr. Reed.
Yeah.
Mr. Reed. Like, so for the vector problems, are we going to do things like, I know last year we did like 2 pool balls that go at like some degree or whatever.
Yeah.
That can each other. We do that some of those again.
Yeah, that's the plan. In fact, I could go right to it right now. If you're fairly confident with what we're doing here, I can look at, okay, so let's do that then. Let's go right through to 312. Just want to make sure I've got this all covered. Yeah. So, okay. Okay, so page 312. It says a grenade of mass 1.2 kilograms. So do you guys remember this, where you have a grenade that explodes in different directions?
Yeah.
Okay, so I'll do this.
Wait.
I'll do this one. We'll go back.
Yeah, and then, sorry.
Go ahead.
We added the vectors together.
Yeah.
And they exploded, like they go like in 3, 4. Yeah, I remember this.
Okay. All right, so I'll go through this question. We're gonna go back. I'll have you do the practice problems today and tomorrow, and then I'm gonna I'll go into work and energy next then, real quick. And I'll put an assignment out on momentum just so that you have a chance to get another mark and do a good job of another assignment. Okay. A grenade of mass 1.2 kilogram rests on a smooth frictionless surface when it suddenly explodes into 3 pieces. I'm going to do, okay. I'm going to do question 2 on 314, which is this question, except it adds into the fact that the first beforehand, there is momentum. Okay. So here's what happens. The grenade is, I don't need this for now. Okay. So in question 2 on page 314, it asks you to do this exact same question. Instead of it being at rest, it's now moving at 1.5 meters per second to the east. Okay, so I have an initial momentum here. Okay, this grenade's been thrown. It's moving at 1.5 meters per second to the east. It explodes into 3 different pieces. So P equals P1 prime plus P2 prime plus P3 prime. We're given P1 prime and P2 prime. P1 is 0.5 kilogram, goes to the north at 3 meters per second, and P2 goes 0.3 kilogram, goes off southwest at 4 meters per second, and it wants the horizontal speed and direction of the third piece. Okay, so if you recall, I have to arrange this differently. I need to find P3. So I go P minus P1 prime minus P2 prime. So what I need to do right now is draw out the individual vectors for this. Okay? So my P is 1.2 times 1.5 gives me 1.8 kilograms meters per second east. Okay? P1 prime is 0.5 times 3 meters per second to the north, but I need the negative of it. So I'm going to make it to the south. That's negative P1 prime. This is negative P2 prime. And the next one is flies off at southwest. So I'm going to make it northeast. And it's 0.3 kilograms at 4 meters per second. So 1.2 kilograms meters per second. All right. And this is going to be northeast. Okay, so I now need to solve this using my vectors. And again, I'm more partial to using the X and the Y. Find your horizontals and your verticals. You can draw it out if you like, but I'm going to do it this way. So now I need, this is 45 degrees right here. So I need the sine of 45. Make sure I'm in the right mode. Make sure your calculator's in degrees. So I go sine 45 times 1.2, 0.849. So this is 0.849. That's north. 0.849. That's east. Okay. So I've got north and south, and I've got east and east. So I know it's going east. Add these together. Subtract this because this is moving south. So 1.5 minus 1.5 minus 0.849. So 0.651. So to get my third piece, I have 2.649 squared plus 0.651 squared. I get 2.728 kilograms meters per second. I need my angle. So second function tan 0.651 divided by 2.649. So, and to find out the speed of it, I would divide by the mass of it. The mass is 0.4 kilograms, so 2.728 divided by 0.4. So it should fly off at 6.82. Okay, so we somewhat remember how to do this. So first thing I do is I rewrite my equation because that tells me how to add my vectors together. Draw out the individual vectors. Because I have negatives on them, I drew these in the opposite direction they were moving. I added all my x's together, my east and my east. I subtracted my y because one was south and one was north. Got that? Used Pythagorean theorem to get my P3 right here. And then divided by the velocity, or divided by the mass to get the velocity. Okay, so since we did this, so let's go through. So page 303 and 304, 1 to 5. So we'll do that today. And I'll look at those answers with you tomorrow. And then we'll move on to work and energy, which I'm going to have to do some photocopying and send out some sheets to you again. Okay? Yeah, we had to go through this because we have to look at elastic collision problems in kinetic energy. So that's why we wanted to go through the momentum and do the refresher on it. Okay? Any other questions today? Comments, concerns? Are we all right?